Artificial intelligence is frequently imagined as a weightless network of algorithms operating invisibly in the cloud. In reality, the physical expansion of global computing power is strictly bound to the massive physical extraction of raw industrial Earth. Training and operating complex large language models requires gigawatt-scale data centers. Supporting these hyperscale computing workloads demands an immense expansion of high-voltage electrical infrastructure. Driven by the energy transition and hyperscale computing, global copper demand will surge 50% to 42 million metric tons by 2040. Because primary mine pipelines aren't expanding fast enough, this creates a structural deficit of 10 million metric tons within 15 years. Secondary recycling cannot mathematically close this gap. Copper installed in legacy building architecture and mid-century power grids has an in-use lifetime of 50 to 75 years. The heavy scrap required to buffer today's market will not be available for recovery until the final decades of the 21st century. Expanding the architecture of artificial intelligence therefore requires an aggressive scaling of primary mining operations. The 21st century contest for digital sovereignty relies entirely on drastically expanding the virgin extraction of a 19th century metal. Inside a data center, algorithmic computation directly translates into thermal energy. A traditional enterprise server rack generates a predictable, manageable heat load. A rack packed with advanced processors optimized for AI workloads produces an entirely different thermal environment. Standard cloud computing racks draw between 5 and 10 kilowatts of power. Next-generation AI racks pull up to 120 kilowatts per rack. As electrical current flows through a conductor, its inherent resistance generates heat, governed by the formula I²R. Pushing 120 kilowatts through highly concentrated circuitry exponentially multiplies this heat. The sheer density renders traditional air cooling useless. Fans cannot dissipate thermal energy fast enough to prevent catastrophic system failure. Hyperscale developers are forced to implement direct-to-chip liquid cooling architectures. These systems pump specialized coolants directly over the processors to absorb and route away the intense thermal load. Managing this thermodynamics requires materials with extreme physical properties. Excluding silver, copper possesses the highest electrical and thermal conductivity of any metal. It is the only viable material for manufacturing the intricate cold plates, heat exchangers, and heavy electrical busbars required to sustain these racks. Because AI training runs require continuous, uninterrupted power for months, facilities implement heavy redundancy, duplicating every piece of power and cooling equipment. This architecture drives the material intensity of a hyperscale facility up to 47 metric tons of copper per installed megawatt. When developers construct a massive 1-gigawatt AI campus, that single facility physically locks in 50,000 tons of copper purely for internal computing and cooling infrastructure. The raw computational expansion of artificial intelligence is strictly bottlenecked by the laws of thermodynamics. Algorithms can only scale as fast as copper atoms can move heat and current away from the processors. Delivering continuous gigawatt-scale power to these isolated data centers requires an immense expansion of the external high-voltage electrical grid. The central irreplaceable nodes of the bulk transmission system are large power transformers. These massive units step alternating current voltages up or down to allow electricity to travel long distances efficiently. This structural cross-section of a 500 kilovolt large power transformer reveals a steel core wrapped extensively in high-purity copper windings. To prevent overheating, these internal windings require a massive cross-sectional area, meaning a single 750 megavolt ampere unit demands 111 metric tons of pure copper just to operate safely. Connecting these substations to high-density load centers introduces a secondary constraint along the physical transmission lines. Standard overhead transmission lines utilize lightweight aluminum cables, allowing the open ambient air to naturally cool the metal. But as infrastructure pushes into dense urban environments, transmission lines are increasingly forced underground. This chart compares the copper intensity of high-voltage transmission against localized underground distribution. Burying cables alters the material physics entirely. Inside narrow, insulated subterranean conduits, cables lose natural convection cooling. To prevent insulation failure, underground 500 kilovolt lines must utilize massive, highly conductive copper cores. Burying a 500 kilovolt transmission line requires 109 metric tons of copper for every single mile constructed. Modernizing the electrical grid to support AI demands an exponential increase in localized copper density. The legacy power infrastructure built over the last century lacks the physical mass necessary to carry this new load. Every single ton of this highly conductive metal required for the AI transition originates deep within the Earth's crust. Approximately 75% of the world's copper inventory is extracted from a specific geological structure known as a porphyry copper system. These systems form along tectonic plate boundaries. When oceanic plates subduct beneath continental crust, intense pressure forces high-temperature magmas to ascend, precipitating copper across a massive subterranean network. This diagram illustrates a porphyry deposit's telescoped layers. Near the top is the supergene blanket, which fueled 20th century industrial expansion. Over millions of years, acidic rainwater leached copper downward, naturally concentrating the metal into dense, shallow bands, where grades routinely exceeded 1.5%. The central crisis of modern mining is that these cheap, high-grade supergene reserves have been functionally exhausted worldwide. To maintain production, the industry has been forced to pivot downward, bulk mining the deep, massive hypogene core at the bottom of the system. The copper within this deep rock is microscopically disseminated. The average grade of this hypogene ore yields a mere 0.44%. Maintaining static copper output now requires excavating and milling exponentially more earth from significantly deeper pits. This severe degradation in ore quality permanently destroys the historical elasticity of the global copper supply. The geological exhaustion of high-grade ore is the physical constraint driving the projected 10 million ton macroeconomic deficit. Bridging a supply gap of that magnitude requires the rapid, synchronized deployment of 16 to 20 new world-class copper mines. This graph ranks the top 5 undeveloped porphyry copper deposits globally, highlighting an exceptionally thin pipeline. The Resolution Copper Project in Arizona holds 10.2 million metric tons, but sits at an extreme depth of 7,000 feet, requiring highly complex, deep shaft engineering just to access the ore. Because of strict environmental regulations, complex financing, and intense engineering demands, permitting and developing these deep shaft operations routinely takes between 15 and 30 years. Extracting the ore is only the first bottleneck. The supply chain tightens further at the midstream processing stage. While mining operations are globally dispersed, smelting and refining are heavily centralized. China currently controls 50% of the world's refined copper production and has accounted for 75% of all new global smelter capacity since the year 2000. The transition from ambitious software modeling to physical AI infrastructure is gated by a highly concentrated, decades-long geological supply chain. Western capital cannot simply accelerate its way out of a physical mining bottleneck. There is an unbroken physical chain connecting the extreme depths of the Earth's crust directly to the silicon of a hyperscale server rack. The development of artificial intelligence is a heavy industrial mobilization. It is a massive physical undertaking disguised as a software scaling exercise. Technology conglomerates view AI supremacy as an existential corporate imperative. Because their demand for materials is highly inelastic, they will aggressively outcompete civilian grid modernization efforts to secure scarce copper supplies during physical shortages. National digital sovereignty cannot be secured by writing better code. It depends entirely on the physical acquisition of the raw materials required to house and transmit that code. The ultimate pace of the global digital transformation will not be dictated by algorithmic ambition. It will be bound by the thermodynamic limits of copper atoms and the unyielding geological realities of the Earth's crust.